Welcome back to Differential Calculus. In this video, I wanted to talk about limits of integration. Or more specifically, I want to talk about the properties of the limits on a definite integral. We know that the limits of integration are the thing that makes the integral the definite integral, right? The a and b in the integral from a to b of f of x dx, which we can evaluate using the fundamental theorem of calculus to be f of b minus f of a. When we've seen the integral previously, when we established the idea of the integral, we've talked about wanting to know the area bound by the curve on the interval from a to b. And so implicitly, we have always said that a is less than b. But that's not, strictly speaking, necessary. We could do it in the other order. And so I'll give you two ways of thinking about what happens if the larger value is the lower limit of integration and the smaller value is the upper limit of integration. Well, the first option is to follow the fundamental theorem of calculus, which tells us that this is going to be f of a minus f of b. Well, that's the same things that we had before, just in the backwards order. And when you change the order of subtraction, it makes the opposite. If f of a minus f of b is positive, then f of b minus f of a is negative, and vice versa. But now that we've done that, we have the same integral from a to b of f of x dx that we're accustomed to, but with an extra negative in front. Ideally, this is a rule that never comes up. But the moral of the story is that we can deal with it. There is nothing inherently that requires the lower limit of integration to be smaller, the upper limit of integration to be larger. When it's not the case, we say that the limits of integration are degenerate. It's one of several ways we can have degenerate limits of integration. And we move on from there. So we're not going to go out trying to set this up. Every now and then it just shows up based on the properties of the particular situation that you happen to be looking at, and knowing that you can deal with it and you don't really have to think about it, I guess it's a place you can breathe a sigh of relief. The other way that I want to think about the same idea is geometrically. When we established the definite integral in the first place, and called the definite integral an area under a curve, I looked specifically at what happens in positive or in negative regions. And we said that the area between the curve and the x-axis below the x-axis is a negative area, and the area between the curve and the x-axis above the x-axis is a positive area. One way you can think about that is that whenever you're moving downward, you have a negative length. And whenever you're moving upward, you have a positive length. Well, why not do the same thing for the x-axis as well? If you're moving from left to right, then you have a positive width. But if you were to move from right to left, you would have a negative width. And so there it is. when the value of the function is positive, the length measurement is positive, and when your lower limit of integration is the bigger number, that means you're moving right to left, which means your width is negative. Positive times negative would give us negative area, not the positive area we expected. Likewise, negative times negative would give us a positive area, not the negative area we were expecting. So geometrically, we can interpret that degenerate case without too much issue. On to the next one. Consider this piecewise defined function. F of x is equal to x squared for 0 less than or equal to x less than or equal to 1, and f of x is equal to 3 minus x for x between 1 and 3. Geometrically, give myself enough space here, we know that x squared is going to be a parabola, and 3 minus x is going to be a line. This function is not continuous. And yet, that doesn't stop us from defining the area under the curve. In this particular case, there is a vertical wall. And trying to figure this out on the whole is very difficult, right? The total area is going to be the integral from 0 to 3 of f of x dx. And because my function changes midway through, that's not something I can figure out. But we know, when dealing with area, that you can split a region up into simpler regions, calculate the area of each, and add the areas together to get the total area of the region. So we can take that area and separately calculate the integral from 0 to 1 of f of x, and the integral from 1 to 3 of f of x. And in those regions, my piecewise defined function settles down. Between 0 and 1, the function is just x squared. Between 1 and 3, the function is just 3 minus x. The integral of x squared and antiderivative is 1/3 x cubed. An antiderivative of 3 minus x is 3x minus 1/2 x squared. We'll have 1/3 times 1 cubed, which is just a third, minus 1/3 times 0 cubed, which is just 0. This last one is a lot messier, but we'll take the time to write it out carefully. I've got 3 times 3 minus 1/2 times 3 squared minus 3 times 1 minus 1/2 times 1 squared. So we've got 1/3 plus 9 minus 9/2 minus 3 plus 1/2. 9 minus 3 is 6, minus 1/2 plus 1/2 is minus 8/2, and then there's also plus 1/3. 6 minus 8/2 is 6 minus 4. So we're looking at 2 plus 1/3, which comes out as 7/3. All right. Answers only a mathematician can love. The fraction arithmetic is tedious, but I hope that there's nothing difficult here. I'm not going to go into an example on this one, but I do also want to point out that this rule always works. If you have the integral from a to b of f of x dx, that's going to be equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And the crazy thing about this is that it still works whether or not c is inside the interval. Because if c is outside the interval, that means that c is either smaller than a, which makes this one turn out to be negative, or bigger than b, which makes this one turn out to be negative, and you cancel out all the things that you double counted. Why that is useful, again, we never seek out to do that. We tend to use this rule in those situations the other way. If the situation that you are dealing with, the thing that you have set up, has the same integrand with completely unrelated limits of integration, where you just happen to have one thing that matches up between them, then you can simplify and make things work and go down from having two integrals to having just one integral, which is faster. Next thing on my properties of integrals. What if the lower limit and the upper limit are the same? The integral from a to a of f of x dx. Again, we can think about this either geometrically or analytically, and we should get the same answer. Geometrically, the integral from a to a asks us, what is the area in that region, which is an infinitesimally small line? Well, you have a rectangle with no length, or with no width, so the area is 0. Or you can think about it using the fundamental theorem of calculus. This is f of a minus f of a, which is also 0. So you can use this to your advantage. One last property. This one is a little bit more challenging to see. Let's assume that f of x is an odd function. Remember that an odd function, I generally think about the power functions. So x cubed looks like this. If you take the y equals minus x line and rotate the lower half around, you'll get it to match up exactly with the upper half. Another thing that a lot of people like to think about when we think about odd functions is the sine function, which I think is actually a little bit easier to see in this particular case. So let me draw a sine function here real quick. And I want to take the integral from negative L to L of f of x dx. And the key here is to notice that the limits are symmetric. Negative L, positive L. You are the same distance away on the left of the y-axis as on the right of the y-axis. And because we have an odd function, the shapes of these two areas are going to be the same. Just one is above the x-axis and the other is below the x-axis. And so the part below the x-axis is a negative value, the part above the x-axis is a positive value, but it's the same value. And when you add a negative and a positive of the same value together, you get 0. That's what the definition of a negative value is. So this is very situational. If you are dealing with an odd function and you have symmetric limits of integration, the integral is 0. Period. End of story. You're done. And while you might think at first, you've studied even and odd functions, and you learned at that time that while there are some even functions and there are some odd functions, most functions are neither even nor odd. So it can't be that this shows up so much as to be worth even thinking about. But one of the poster childs for the odd functions is sine. Sine is an odd function, and sine shows up a lot. Another poster child for the odd functions is the line, y equals m times x. That's another one that shows up a lot. Whenever you have symmetric limits of integration and you have one of those things showing up, the result is 0. Period. End of story. You don't have to think about it. You don't have to do any work. Just say that you are taking an odd integrand and you are evaluating over symmetric limits of integration. The result is going to be 0 every time. All right. I'm going to end with one that's a little bit outside the box. F of x in this case is not odd. We cannot use that odd property, which would make life a lot easier if we could. Or, at the very least, we don't know that f of x is odd. But we do know that the thing we're looking for is not just f of x, and it's not just one integral. We want the integral from 0 to 7 of f of x minus the integral from 3 to 7 of f of x. And I want you to use properties of limits to rewrite this using a single integral. And I will give you 2 hints. Honestly, it's kind of giving the game away, but if you want to try without the hints, you can stop the video right now. Otherwise, take note of the fact that the argument of the integrals is the exact same, f of x dx, and take note that the upper limit of integration is the same 7. Try to use those things to your advantage and use the properties that we've talked about. See what you can do with that. And I'll see you in the next video.